All right, let's talk about one-sided derivatives. We're going to see some vocabulary here, differentiable on a closed interval a to b. And in order to define that, we're going to need to define a couple of smaller terms, right-hand derivative at a and left-hand derivative at b. There will be no new theorems or rules. So we begin like this. A function y equals f of x is differentiable on a closed interval a to b if it has a derivative at every interior point of the interval and if these two limits exist at the endpoint. These limits are the limit as h goes to 0 from the right of f of a plus h minus f of a over h. There is a difference quotient. And the limit as h goes to 0 from the left of f of b plus h minus f of b all over h. There's the difference quotient again. So here's what we're thinking about. If there exists some function that begins at a and ends at b, or at least it exists through them, we want for there to be differentiability between a and b every point in the middle, but we also want there to be right-hand differentiability at a. So coming into a from the right, are we differentiable? And then we want there to be left-hand differentiability at b. So coming in from the right side of b, do we have a derivative? And if we're differentiable at a and b and every point in the middle, then we are differential on the entire closed interval. So to take one-sided derivatives a bit further, here is a graph that kind of mimics what I drew on the last slide. We have a function that moves from a to b, and it is continuous throughout. We have differentiability at every point in the middle. Now on the left end point A, we see our a plus h x value to get our y value. And there's our secant line drawn between. And we're moving that point a plus h closer and closer to a so that our secant slope turns into a tangent slope. On the right side, here's our point B, and B plus H is to the left because we want to come into B from its left side, and that means that H is negative there, and then this secant line is going to move closer and closer and closer into B so that we become a tangent line. Now, this is important as well. Right-hand and left-hand derivatives are not only defined at endpoints of intervals, but they can be defined at any point in a function's domain. To emphasize that, we have this usual relationship between one and two-sided limits that also holds for derivatives. So when we say the usual relationship between one and two-sided limits, here's what we mean. We mean that the two-sided limit, so limit as x approaches a two-sided of a function, is equal to L some limit if and only if both the left-hand and right-hand limits are equal. So if and only if the limit as x approaches a from the left is equal to the limit as x approaches a from the right, and both of those need to be equal to the same piece over here. Well, that limit statement also holds true for derivatives. So it allows us to conclude that a function has a two-sided derivative at a point if and only if the function's right-hand and left-hand derivatives are both defined and equal at that point. So here's an example indicating this or emphasizing this. Show that the following function has a left-hand and a right-hand derivative. So it has both left and right derivatives at x equals 0, but no derivative there, which means it's not differentiable two-sided at x equals 0. So let's get started. The point is 0, and we can kind of envision this graph doing one thing, x squared, to the left of 0 and then to the right of 0 doing another thing. And so at 0, we would want to come in from the left side here with the x squared term. So let's set up a limit as h goes to 0 from the left. So we're going to look at the left side of 0 of f of 0 plus h minus f of 0 all over h. Well, if we plug in 0 plus h to the function that exists on the left of 0, then we are looking at what? Well, 0 plus h squared is, well, h squared. So this is the limit as h goes to 0 of h squared. If we plug in a 0, we get 0. And if we leave that h on the bottom there, we get an h. Well, this now simplifies into a limit as h goes to 0 of just an h, and that, of course, is 0. So the left-handed derivative at 0 is 0. Well, what about a right-handed derivative? So coming in this way, well, let's take a look at that derivative. So the limit is as h goes to 0 from the right of f of 0 plus h minus f of 0 all over h. So if we plug in 0 plus h to this function right here, we get 2h. So this is the limit as h goes to 0 from the right of 2h. If we plug in 0, we get 0, and that's over h. Well, those h's can cancel, and now we're at the limit as h goes to 0 from the right of 2, and that's 2. So the left-hand limit exists, and it's 0. The right-hand limit or derivative exists, and it's 2. So I should put those minus signs here to show left, and we have the plus signs here to show right. Those derivatives exist, but is there a derivative at x equals 0? In other words, is there a point y prime of 0? And the answer is no. This does not exist because the left-hand derivative and the right-hand derivative are not equal. And that finishes the video series for section 2.1.